Hello again and welcome to the York College of Pennsylvania pre-lab series. This pre-lab video is for the copper reduction and recovery experiment, part of the General Chemistry 1 sequence here at York College of Pennsylvania. Today we're going to be considering how we're going to obtain a sample of copper from solution using redox chemistry or oxidation reduction. Let me show you the actual reaction that we're going to do. We're going to be using a blue colored solution, copper 2 sulfate, and zinc metal. So I'm going to get it started right away. Just simply putting the zinc into the solution will cause the reaction to occur, but it takes some time, so I'm going to get it started and leave it sit in the hood while I explain some of the materials and some of the background of the experiment that we'll be doing today. So oxidation and reduction are two processes that occur together simultaneously, and oxidation is the process when electrons are lost by a species. So what I have here is a little reaction showing zinc, which is being ionized and giving up 2 electrons in the process of being ionized. So that's what we call oxidation. On the other hand, these 2 electrons can't just hang out and be free. They have to be gained by something. So if we had a copper ion, for example, it could pick up those 2 electrons and be reduced. And so we often use a little acronym to help us remember what's happening in this process. Oxidation is loss, reduction is gain, referring to the electrons. So this is called the oil rig. Another one is Leo Gur. Gur, sort of a sound that a lion makes, Leo being a lion. Loss of electrons is oxidation, gain of electrons is reduction. These two have to happen together so that you don't build up electric charge in your reaction system. All of the electrons lost must subsequently be gained by another compound. And so in today's experiment, we're going to have this exact setup of oxidation and reduction by bringing the copper from a solution of CuSO4. So really we have +2 copper and then metallic zinc. So this will be aqueous and this will be solid. And we will produce ZnSO4, which is now the aqueous and solid copper. So our copper will transition from being a +2 to a 0. It will be reduced, and our zinc will begin as metallic zinc 0 and end as +2. So the zinc will be oxidized and the copper will be reduced. When it's all said and done, the copper will be as a solid in your reaction container. And so you'll be able to recover it, hence the title of our experiment today, Copper Reduction and Recovery. And so let me show you some of the apparatus that you'll be using as part of the experiment today, and make sure that we're all set to safely conduct the exercise. So the main goal will be to get the copper out of the solution. And if I come up in front of the camera now, you should be able to see that we're starting to form copper on the outside of the piece of zinc. So in this case, we're really just coating the copper onto that zinc, and I could literally wipe that copper off of right there. So we're going to use a very fine zinc powder to maximize the amount of copper that we recover. Technically, this has like a thin strip of zinc still on the inside of that copper coating. When you're all done today, you'll have a bunch of copper filings that'll look like in your solution, and so you'll want to separate them out, and we'll use a filtration apparatus. And so I've set up a filtration apparatus today. Let me zoom in and make sure you're seeing it in great detail here. Okay. The filtration apparatus is composed of what we call a Buchner funnel. It has tiny holes in the porcelain part of the funnel, a plastic disc which allows us to get suction, and then a filter flask or sidearm flask that has this arm on the side. So we assemble it by placing the funnel into the vacuum apparatus on top of the filter flask. Notice that I've clamped my filter flask down. That's because the hose tends to want to twist the filter flask, and so it would fall over in the midst of being used. And then this hose is connected to a vacuum line. In your hoods in the lab, the vacuum lines will be at the back of your hoods, so look for them there. And there's a knob, or that you would use to turn on, a lever that you would use to turn on and off the vacuum. Inside the funnel, you would need to place a piece of filter paper. And so during the lab today, at one point, you'll weigh a piece of filter paper. You'll need it pre-weighed, and then you'll put it in there, and you'll be collecting the contents of your reaction. You would pour through. I won't do it right now, but you would pour them through, and the solid remnants would remain in your filter flask that way. Okay? And it's a simple matter of letting that air dry and subtracting the weight of the empty piece of filter paper to discover the mass of the copper that you've recovered. Along the way during the lab today, there'll be a couple of hazards to be concerned about. Let me briefly explain a couple of those, and then we'll go through the pre-lab questions to get you all set for the pre-lab. You'll be working with some strong acid at some points, so please be careful about how you handle the hydrochloric acid. And you'll also be working with two volatile solvents, an alcohol and acetone. These are used to dry the copper, to remove the water from them. They're very polar compounds, and so they have the ability to grab hold of little bits of water that will be attracted to your copper filings that you'll have. And we want to remove that because we don't want that weight in our final mass calculation that we're doing. And so we'll pour these solvents over top of our copper, but we want to make sure there's no flames, no ignition sources nearby, and you'll be working in the hood at that point. So it'll be best if you have your entire apparatus, like I just showed you, set up inside the hood. Okay. All right, I'm going to go through the pre-lab questions because they're a great model of a few of the calculations that you'll be doing in today's lab. Ultimately, you're going to want to know what's the percentage of the copper that you've recovered from the solution that you begin with. And you'll want to quantify that as a percent yield. And so we have really three steps to doing that. You'll be preparing a solution of copper 2 sulfate at the start of lab, and you're asked to check your calculation with your instructor before you begin your actual work. So the pre-lab questions mimic this by substituting for the copper 2 sulfate a solution of silver nitrate. So we're asked what mass of silver nitrate is needed to make 250 milliliters of 0.125 molar solution. So molarity is found by taking the moles of the solute, the silver nitrate, divided by the volume of the solution. So the mass would then be the moles, it would be related to the moles, and so we could find the moles of silver nitrate by taking molarity of the solution times the volume. So 0.125 moles per liter times 0.25 liters is our molarity, our moles. And so then this actually we could multiply. I don't even need to get the intermediate answer because I know the units here will be moles. I could multiply that by the molar mass of silver nitrate, 169.88 grams of AgNO3 per 1 mole. And this will give us the mass, when we're all done, of 5.31 grams of silver nitrate. Now when we prepare this solution, the volume is key and you'll be using very carefully calibrated volumetric glassware today. You'll use the glassware that looks like this with the round bottom. This is called a volumetric flask, as opposed to an Erlenmeyer flask, which has the more wide sides like that. All right. So we don't want this because their volume markings are much more inaccurate. This type of glassware has only one volume marking on it, and so you'll choose one well, for the appropriate size that you're indicated in the lab today. So our second question is, what mass of silver is present in this actual solution? Because this mimics the mass of copper that we could expect in our lab today to extract from our solution of copper 2 sulfate. So of this 5.31 grams of silver nitrate, how much of it is actually silver? There are a few different ways that we could solve for that actually, but one way is to just use the molar mass that we have right here and understand that within this molar mass there are 1 mole of silver. And so we can take our 5.31 grams of AgNO3, and for every 169.88 grams of AgNO3, there are 107.87 grams of silver. That's because there's 1 mole of silver in 1 mole of silver nitrate. So our grams of silver nitrate are eliminated, and we can convert to grams of silver. So we get 3.37 grams of silver available. So if you were working with the silver nitrate solution, you could expect to extract 3.37 grams of silver. And then the last question says, well, what's the percent recovered yield? So how good was your work, in other words, if you actually only get 2.86 grams of silver? And so the percent recovered or percent yield is the actual yield divided by your theoretical yield times by 100%. This is not quite the same as a percent error calculation. So this is 2.86 grams of silver divided by our 3.37 grams times by 100 gives us an 84.8% yield of silver. I would expect that's about where we should be for an experiment like what we're doing today. There are a couple of errors potentially waiting to happen in our work. Number one is when I showed you the piece of zinc, the copper was technically only coating the outside of the zinc. And so we might not be reacting 100% of our zinc. So if you don't react all of your zinc, you might not get all of the copper that you would expect to recover. So that's a little issue to consider. Right? There is the potential to lose some of our mass of copper through the filtration apparatus that I showed you if we're not careful with how we filter. There is the chance that if you weigh your filter paper when it's too wet, it will be heavy, and thus you would have an artificially high mass of copper, apparently. When you subtract the final mass of the filter paper and copper minus the original dry mass of the filter paper, you've got additional water weight that in your calculations is going to look like copper. So that could inflate your copper mass and your percent yield. And then there's the issue of the source of the water that we use. We're going to use distilled water, but if you were to accidentally use tap water has a variety of other ions dissolved in it, and occasionally you might have some copper ions in your water. And if those were in the water, they could come out of the solution reacting with the zinc, just like the copper that we've added with our copper sulfate. So that could give you a higher percent yield if we had a water supply that wasn't clean of those ions. But we're going to take care of that issue hopefully with our distilled water. Okay. So I think I've covered everything today. Careful of some of the safety concerns. There's really not a great need to wear gloves today, but if you'd like to, feel free to wear gloves. Of course, have your safety glasses on. You'll be working in the hood most of the time to take any fumes that you generate. You will generate some hydrogen gas at one point when you eliminate your excess zinc. So be careful to work in the hood and pay attention to all the safety instructions provided by your lab sections instructor. Thanks for watching. Hope you've got the pre-lab questions down and enjoy the experiment.